on going over the implementation of AES, which I showed you in the press using this nice graph. And I'm going to try to find, again, my mission is to find a place where the state depends on the plain text and a small amount of the key. I don't want a huge amount of the key, because then I will have a very, very hard time processing it. I want like a reasonable amount of the key. So let's begin looking at the evolution of the state over time. And the question I'm going to be asking you, at each point of time, how many bits of the key affect each bit of the state? So one bit of the state, how many bits of the key affect this single bit, right? So we're going to look at the cipher as it's evolving. Why can I only look at a single bit? Because I only know how to split into two. I only know to split into two piles. This is how I do distance of means, right? I can only use one bit of the state because I can only compare two batches of traces. So now we begin. I'm going to start evolving the state from the beginning. So let's begin at the first time where I encounter AES. Now I just fed my plain text into the state register. So I just copied the plain text into the state register. So how many bits of the key affect? I just choose an arbitrary bit in the state. Let's choose the first bit of the state. How many bits of the key affect the first bit of the state when I just fed in the plain text? So the answer is 0. Who would like me to repeat and explain the question I just asked? Who would like me to repeat the question? Okay, so I'm going to repeat the question. The question I wanted to know is, if I take one bit of the state is 128 bits. If I take one bit of the state, how many bits of the key affect this single bit of the state? So I began when I just fed in the plain text. So obviously, the key is not a factor here at all. So the key is not affecting the state in any way. So let's continue. Now the first thing I'm doing, could the intermediate point be a XOR of 3 bits of the key in the message? Yes, I'm just going over this all right now. This is what I'm doing literally right now. So when I'm looking at this is a bad place to look at because the key is not plain at all. Now let's look at the next one. I XORed. The first thing I do is add key. I XORed the key to the state. Now, think carefully and tell me, how many bits of the key affect the first bit of the state, bit number 1 of the state? How many bits of the key affect the first bit of the state? Right, so the answer is only 1 bit of the key affects 1 bit of the state. And because we just XOR 1 bit with 1 bit. And this means that looking at this point is not so good because of the linearity. So I might have time to cover it in the next hour. What this means is that I can only get a very little amount of data out of this as an attacker. Because I only get 1 bit out, it means that all of the other bits are going to be driving increasing. So the next operation I'm going to look at is subbytes. So subbytes, I take this lookup table and I substitute the single bytes of the state with the values. So the first bit, this one is a little more tricky. The first bit of the state after subbytes, how many bits of the key affected? Right, so the answer is 8, and I'm going to explain why 8. because 8 bits of the state went into the lookup table. So this 1 bit of the state is affected by all of its inputs, because this is how the S box works, which means actually this is a pretty good place to put our hypothesis, right? So 1 bit of the state is affected by 8 bits of the key. 8 is nice. We can still brute force 8 bits, and it's because it's nonlinear. We can also have a nice way of rejecting. So our noise is going to be rejected pretty well. So now the next operation is shift rows. Shift rows, we move the state bytes around. Now you're already answering without me asking. Indeed, after shift rows, still each bit of the state is affected by 8 bits of the key, because we just move the key around. We just move it around. So it's as good as this one. And as I'll show you effectively as an attacker, when you do DPA, you can get actually you look at the before shift rows and after shift rows at the same time. And as I told you, because shift rows is like an imaginary operation, sometimes it's not even implemented. So now the next thing is mixed columns. Mixed columns, you create a linear combination of all of the state bytes in a single column. So here, how many bits of the key are in each bit of the state? OEI is saying correctly that it's 32. And why is that 32? Because now I've mixed in the entire column. So I've put 32 bits of the key in add key here. And now I've mixed everything around. So here I have 32 bits affecting my single state bit. And the problem with 32 is that it's a little more expensive to brute force 32 bits. I guess if you have a really powerful computer and a lot of storage and a lot of time and a lot of motivation, you can brute force over 32 bits. But brute forcing over 256 is much more effective. And now after I add round key, it's completely helpless. Now we could say it's affected by effectively 128, because the round key itself is a function of all of the key bits if it's done well. So after I've done add round key, effectively each bit of the state is affected by 128 bits of the key. So back after that, I don't really have anything to do as an analyst. So the best place to look at effectively is so we start with subbytes. You start with the plaintext, then you do add key, and then you do subbytes of plaintext XOR key. And you can also read about it in the book. This operation is the best one to look at, because it uses a small amount of the key, not too much. 8 bits is not too much, and it's got this nice nonlinearity property, which allows us to reject the falsifier. Why is this? If you look at the single bit of the state here, a single bit of the state is affected by all of the bits in the first byte. If you look at the first bit of the state, this first bit is a function of the first byte of the key. Just look at this operation. Subbytes of plaintext XOR key. You only look at the first byte of the key, but you look at the entire byte. Because, yeah, subbyte is a byte-wise operation. Right. You're answering yourself correctly. Thank you. So I'm going to discuss byte 0. Doesn't really matter, because how am I going to do the attack in practice? I'm going to do a DPA attack on byte 0 of the key, and then byte 1, and then byte 2. And after I do this 16 times, I've done a DPA attack on the entire 16-byte key, and I'm done. I don't need to continue. So I only simulate I don't really simulate, but I only look at the first 2 sub-rounds. Just I do add key and then subbytes. So now we can do the whole Vaizata. I can feed in the entire thing. So, one bit change is not enough. So it's not noise. It's not noise. It's the fact that XOR is linear. What happens if I change another bit in the plain text, it's going to also change the output of the XOR. So think about it. What if I change another bit? It's going to change the XOR again. It's going to change it linearly. So it's going to be very difficult for me to reject guesses, but it's something that it's best seen when you do it experimentally. Right. So here is Vaizata for DPA of AES. The first thing I need to do is make a simple assumption about the implementation. And I'm going to make the simplest possible assumption that you can make about a device. That is this. The power consumption is a function of the data. What function? Linear function, nonlinear function, function of the Hamming weight, function of the Hamming distance, something else, nothing. This is the simplest assumption I'm going to make. I don't have right now the statistical richness to make any more complex assumption, and also it's complicated enough as it is. I don't want to make any more. So I'm just saying the power consumption is a function of the data. Okay. Now the next thing I'm going to do is guessing a little part of the key. Now, when I was doing timing attacks on Montgomery, I could guess a single bit of the key because the exponentiation was bitwise. But AES is not bit-oriented, it's byte-oriented. So I'm going to have to guess a byte. I'm going to guess byte. How many possible guesses do I have for this byte? Indeed, I have 256 possible guesses for the byte. Right. So, and when I was doing the timing attack, I had two hypotheses, two competing hypotheses. I had two ways of splitting my batch of traces into two groups. I have the split which is supported by the guess 0, and the split which is supported by the guess 1. But here, I don't have two ways of splitting. I have 256 ways of splitting. So I have 256 key guesses. So I have 256 competing hypotheses. Only one of them is correct. All the other ones are worthless, are garbage. They don't give me the key. They are actually wrong key guesses, incorrect key guesses. So I'm trying to guess. Could be. These are things I don't know. I learned electrical engineering. I'm a simple man. Could be. Nova. Could be. Maybe if you say that, you'll get higher salary in your job interview. Sounds like something very, very clever. Okay. Okay, I do that all day. Thank you. Thank you. Okay, so I'm going to assume that I guessed my byte correctly. I have 256 possible guesses, but each guess gives me a way of splitting my device, my set of traces into two bunches, right? Two sets, just as I did in the timing attack. I make a guess, and then according to this guess, I split. How am I going to split? In the case of timing, I'm going to say this bunch takes a longer time to run, and this bunch takes a shorter time to run. How am I going to split in the case of DPA? I'm going to say in this bunch, a certain bit of subbytes of plaintext XOR key is going to be 0, and in this bunch, this bit is going to be 1. Okay? 256 possible guesses. Each guess gives me a split into two piles. How do I choose to which pile, on which pile do I throw the trace? I'm going to look at one bit of this state. And now, the question I have to ask you, why should this bit have any effect on the power consumption of the device? Can anybody explain to me why this has any meaning? Why should they get anything out of this split? Why is this good for anything? Should I answer? Yeah, I'll answer. Well, this bit is going to be on the buses. It's going to be loaded and stored and computed and shifted and all that. It's going to be data, which is passed to the device under test. But the power is a function of the data. So if the power is a function of the data, then it's going to be a function of this bit. This bit is part of the data. So the power is going to be a function of this bit. Therefore, I don't know if it's going to be an increasing function, the decreasing function, as I told you, I don't know that. But it's going to be some function of the data. So it means that I can have two bunches of traces, and one of them will have more power consumption, one of them will have lower power consumption. I don't know which one because I don't have a good power model. But if the power consumption is a function of the data, and this is certainly going to be part of the data, then the power consumption is going to be a function of this. And therefore, I will have different power consumption in each one of the piles. Awesome. And then I can do a statistically meaningful. I can do a difference of means. But now there is a little complication, which comes from the fact that I'm doing DPA attack and not a timing attack. And what is missing here is the specification is statistically meaningful, but when? When is it statistically meaningful? You have millions of points. And most of these points, the power is not a function of this because this is not what's going on the bus. Most of the time, the power is a function of something else. So most of the time, I'm going to get nonsense. Only in a very, very small amount of time, very short period, will this data is actually going to be on the bus. And then I'll get a statistically meaningful reading. And as you'll see after the break, the distance of means now is not going to be a scalar. It's going to be a vector because each one of my measurements is also a vector. So you'll see the distance of means is hovering around 0. So I'm going to have a vector called the distance of means. It's going to be 0 most of the time. And then it's going to be, whoop, I have a little peak. This peak is the correct time. And this peak will only appear if I guess the t correctly. A lot to understand, but I'll show you very patiently next hour in my